Hi, welcome back. In this lecture I want to provide a brief description of an application of the method of moments. In particular, we are going to look at the capacitance problem in an unbounded 2D region. So what unbounded 2D region means that we are not going to impose the boundary condition, or probably better to say that the boundary condition of open boundary condition are included in the green function. The problem we want to solve is the following. So we want to calculate the capacitance per unit length of a capacitor. That is depicted here in the picture on the right. So we have two plates at a distance of 8, and then the length of the two plates is W. So we want to calculate the capacitor per unit length of these two equal and parallel conducting strips in a free space. So that means that it's not going to be a boundary condition here. However, we will know what is the difference in voltage between these two plates. So the way to do the calculation of the capacitance is to first calculate the total charge on the two plates of the capacitor. The way to do that is actually what we're going to do is to divide the two capacitors in small elements, and for each element we will calculate the charge density. Then, because we know the volume, the charge density, we will sum it up all the contribution for the charge for these two plates and calculate the total charge, and from that we're going to calculate the capacitance. So we're going to apply the method of moments, MoM, that is particularly useful for this particular problem because it's open geometry, so it's open boundary condition. That's what we call in the title of this presentation unbounded region. So the first step when we want to apply the method of moments is to derive the green function. So the green function for our problem is the following. So we noted the potential from a line charge. So if we have a thread, a line charge, we know what is already the green function from basic electromagnetic courses. The green function, that is what is the potential at the point R with the line charge at the position R prime that has coordinate x naught and y naught. So the green function for this problem is the following. So we have a minus in front, and then we have a rho L, that is the linear density charge divided 2 pi epsilon naught, and then here is important, we're going to have a logarithm, right? So the potential will have a behavior that is following a logarithmic. That is basically the distance between a point where we want to calculate our potential, that is also the observer position, and the position of our source. So we are going to have one source. In our case would be the source on one element, and then we calculate the potential. So this is the distance divided by a constant called rho naught. So roughly speaking, the green function is some rho charge density, linear charge density, multiplied by a logarithm that is a function of the distance of the observers and of the source. So for the parallel plate capacitor, we will have two line sources, right? So we are going to have two plates. So our Green's function will have the two contribution. So one from this plate here and one from this plate here. So we're going to have a terms that is taking account of this. This is the following, and then another term that is taking in account the second plate. So this is the Green's function for calculating what is the potential given two line sources, right? So it's the superposition of the two Green's function for the simple case of just one line charge. So let's go and apply the method of moments. So the method of moments is basically the FEM method. So the first thing we need to do is to divide our domain in different elements. So in this case, we're going to have a capacitor. So we're going to divide the two capacitors. We're going to have two strips of the capacitor. So we're going to divide the strips of the capacitor in smaller elements. So the first step, like in all the methods that we've been seeing so far, is to divide the capacitor plate into elements with the coordinate xi, x plus 1 at the nodes. The second step of the method of moments is to calculate, is to impose the linear basis function. So most of the method of moments use a quite simple basis function. In this case, we're going to use a piecewise constant basis function that is basically hat function. So for each element, we are going to have one corresponding piecewise constant function that is going to be equal to 1 on that particular element and 0 in all the other elements. So very, very simple, right? So even when the linear basis function we'll be using in FEM. So the testing, so that's where we're going to impose our equality condition. The testing will be done as a point matching. So remember that we have two techniques in the momentum methods. One is the point match or collocation or Nystrom method. The other one is the weighted residual. We're going for the first one. And we're going to impose this equality condition at the midpoints of the grid. So if this is xi, this is xi plus 1, then we're going to put in xi plus 1/2 our matching condition. As I mentioned in one of the previous lecture, this is important because if we impose this testing function and no, we will probably have a spurious solution that is something that we want to avoid. So we are going to choose the middle point of our grid to avoid a spurious function. The technique is to integrate the green function, and in this case we can adapt it to two different techniques. The first things we could integrate numerically the integral, or we are going to can calculate, if we know the solution, the integral analytically. So this is our original for one plate the Green's function. So we're going to add it up also the other part later on is this integral here. So we have an integral from the starting point of the plate to the ending point of the plate in the x direction, and then we're going to have a constant a term that depending on the source, and then the part of the logarithmic. So in the method of moments, so what we can do is to split it up, this integral in the integral over the simple domain. So we're going to do the simple domain. The second things that we are going to do is also to calculate analytically this integral. So the first thing we can do, we're going to split. So we go from this integral, big integral, to the sum of all the different element contribution to that particular integral. So we have integral from x start to x end, and then also we have as a parameter d, that is the distance in the y direction. So we can analytically calculate this term with this expression here. In the lecture today, what we're going to use is this analytical formulation. Keep in mind this needs to be calculated for each element, and then we're going to sum it up. Another trick that we can use is to realize that the problem has a high degree of symmetry or anti-symmetry. So if we take into account the left-right symmetry, so this symmetry here according to this axis, and up-down anti-symmetry, so the sign will be inverted, is enough to discretize only the right half of the upper plate. So we're going to take this part here, then we're going to discretize, right? And then we're going to assume that we are having this left-right symmetry and up-down symmetry that will result in additional terms. So we divide this part of the domain into n elements with n points xi, from I going from 0 to n, where n is the number of elements. Then the potential at the point xy from the assumed charge distribution can be written as the combination of the four elements. So the first one is going to be the calculation of the integral coming from this part here. Then we have the contribution from the left part of the domain, that is a symmetry condition, so it's going to be a plus. And then we have two contributions from the bottom plane, so there will be anti-symmetry condition with respect to this one, so there will be a minus sign here. So the method of moments will require us to solve a linear system that we consider A multiplied by R equal to V, so where R is our unknown, that is the charge density for each element, V is the known term, and A is the matrix that we're going to assemble for the method of moments. So how do we set the assembly matrix? Well, we set it by choosing the testing point at the midpoint. So for xi equal to x, so the testing point is in the middle point. For I from 0 to n, where n is the number of elements that we choose. And we do this only for the upper part, right upper part of the capacitor, and then we are going to have 4 other integrals to take into account the whole contribution. So if you do that, our element of the matrix A is the following. So this is element ij. It will have 4 terms, 2 with plus and 2 with minus. In this case, V is the column vector where all the elements are set to the potential on the upper plate. So it's going to be V over 2, where V is the difference of voltage between the two plates. The solution of this system will give the charge density on each element in the vector R. So R is our unknown term that we calculate by solving this linear system. So again, like in the FEM, we form this matrix A that is calculated by calculating all this contribution from the integral, and then we have the term, known term, that is the voltage of the plate. So this can be applied also in general geometries, for instance on curved geometries like depicted on the right part of this slide. So in this lecture we treat a very simple geometry with a large degree of symmetries and plane plates. However, it doesn't need to be that. So it can be also a curvilinear case, like in this case where we have one element, this element here, and a observation point here, which is assumed to lie at the normal distance d from the straight line extension of the element. So in this case, when we calculate the integral, we have one is the x direction, and then we calculated the y direction that we call the d. This is going to be the distance normal to the element. This can be, as I just mentioned, can be generalized to a completely general 2D geometry with no symmetry at all and curved conductors. So the fact that we are not going to have symmetries will not allow us to use the same integral and then sum it up using the symmetry. So we will need to take care of both plates and left and right, bottom and right. In that particular case of geometries with the two line charge, the contribution from this element to the potential at the observation point x ops is the following. So this is the integral. So we go from x start to x end. So we're going to have this integral here that can be calculated analytically. So this is the solution, analytical solution. So then here, by replacing this value here, psi e and psi s in the equation here, we will find the contribution for one element. So what we are going to do then is to calculate the contribution of all the elements and fill the matrix A. So for the assignment, we are going to solve this using the MATLAB codes that consist of basically two files. The first one is setting up the configuration of the capacitor. So we need to set it up, the distance between two plates, the length of the capacitors, and how many elements we want to have. And then we have a second file that is actually performing the assembly of our matrix A by calculating those integral. We know the analytical formulation, so we're just plugging here. So you see the logarithm here and the arcotangent here coming from analytical integration. We assemble the matrix A, and then we calculate the sigma, that is the charge density for each element, by basically calculating the matrix, this linear system A, where A is the matrix and V is the known term. Once we know the charge density for each element, we calculate the charge for each element by multiplying the volume by the charge density of that element. For the assignment, we ask you to implement adaptive strategy. So what you will see by solving the numerical integration of the capacitor problem using the MoM, you will see that the elements in the middle of the strip, where the charge density is small, give a small contribution to the total charge and capacitance. So the one in the middle, they don't really play much role. So most of the charge will be at the edge of the capacitor. So an error at the edge will result in an overall big error of the method. While the error in the middle will count very little because the contribution is very small. So we can do this in a smart way And we can realize that some of these elements would be more efficiently used near the edges. So we might want to have different elements for our element distribution, and we're going to have small elements that are focused on the edges of a capacitor, right? So those we can have quite a high accuracy. So we want to have more elements near the edges where the charge density is high. And for doing that, we're going to adjust the length of an element in adaptive grid. And the technique that what we want to do is really to have the total charge on each element so that is the same, right? So we will try to make a strategy that is for each element the total charge is the same. So that's for the assignment. The bonus exercise of the assignment asks you to explore an alternative to the exact analytical integration that we have been using in the MATLAB code, that is calculating numerically the integral. Right? So we can use numerical integration of that integral with the Green's function and the source term. One of the issues that we're going to have is that there is going to be a logarithmic singularity that might cause some difficulty. Remember that in the Green's function there is a logarithmic. So if we're going to calculate that integral with a logarithmic, the point logarithmic of x for x equal to 0 is going to minus infinite, and it's going to be a singular point. So we need to be careful with that. For the numerical integration, we could choose 4 techniques. So there are 2 techniques that we discussed very briefly in assignment 1 when looking at the convergence test. They are the midpoint integration and the trapezoidal rule. That we look at those in assignment 1 very briefly. In assignment 3, the one with the FAM in 1D, we're looking at just in assignment Gaussian integration. So you probably remember that we choose two particular points when doing the integration. Those were like 2 divided by square root of 3. So those are the weights that are coming from the Gaussian integration. So we touch up on that very briefly in one of the assignment 3 for the first exercise of FAM in 1D. And also there is basically an extension of the Gaussian integration to take into account the logarithmic singularity. So the first technique that we are going to ask you to implement as a bonus exercise is the midpoint integration. So the integral for one element, so we have this is basically our is going to be our Green function. So this integral is basically using just one point for the point in basically at the middle between these 2 nodes, right? So in the case we want to calculate for x equal to 0, this is going to minus infinite, and this integral is going to diverge. So keep in mind that there is a logarithmic in the integral. So if this f is a logarithmic, then this part will diverge. So we will need to take care of the point x was 0. So we could use this technique on our domain, except for x0, where we actually know that is going to be minus infinite. So you might want to use this, but then take care of the x equal to 0 that is going to diverge. A second technique is called the trapezoidal rule. In this case, we're going to use 2 points that are equally distance from x, and this bring us is nice because we don't need to calculate anymore this function at the point 0, right? So we basically avoid the singularity by adding +1 plus h over 2 and minus h over 2, right? So we calculate the function in these 2 points. However, you will see in your calculation that the error is quite big. The Gaussian integration is very similar to the trapezoidal rule. So we are going to calculate the f in 2 x points that are equidistances, but they are not at the distance of h over 2. However, they are calculated in 2 special points that are h2 over 2, but this is also divided by a square root of 3, so even closer to the point. Also, this technique gives quite a big error when calculating numerically the integral. The fourth point is a technique to deal with the logarithmic singularity. Is an extension of the Gaussian integration. So you see, still we evaluated the function in 2 points, x1 and x2. But at this point, we, instead of dividing by the square root of 3, we divide it by e, right? So that is the natural basis, logarithmic basis. So this is the last slide. Is also the last slide. I have a lecture about the MoM. Thank you very much.